Okay, so now let's talk about this idea of parallel transport of a vector. Right. So the idea is more or less that, as you might imagine, the idea is that if I give you an initial vector at a point and I consider a curve, it's like which goes through that initial point, I want to be able to move that vector, it's like along that curve in such a way that the vector doesn't change, so to speak, right? So that's what I mean by parallel transport of a vector, right? So I want to, so given a vector, let's say A, which is in the tangent space to C, right? You want to transport it to T cos C plus D cos C without changing it intrinsically in some sense. Okay, so if you have now 2 points, right? Let's say cos P and cos C prime, I'm going to imagine having a curve which connects the two, which is, you know, parametrized in some way. Let's say cos C of T, right? So we have a curve cos C of T connecting 2 points on a manifold, and I want to transport the vector from one point to the other along this curve while keeping it constant, for lack of a better term, right? While keeping it sort of constant, right? So that's what I would mean. It's like by parallel transporting, it's like a tangent vector, say at the initial point along this curve to the final point. Okay. So I'm going to define, it's like a vector which is defined just along this curve. So I want a, which is a function of t, right? And the t is, again, it's like induced, it's like by this parametrization. So a of t is going to be in the tangent space of c at t, right? And a of t is going to be ai e sub I cos c t, right? So what does it mean? It's like for it to be constant, is that, you know, it's like this assignment, it's like of this vector at every point along this curve is going to be such that when I take its covariant derivative of this a in the direction of the curve, it should vanish, right? So that's, you know, the natural notion of what it means to be constant, if you will. It's like along the direction of the curve. Okay. So, so for a of t to be sort of constant along c of t, right? What you want is to have that the covariant derivative of a in the direction cos c dot equals to 0. Okay. All right. So as before, we can write that in coordinates. right? What does that really look like? So again, let me just briefly remind you of what sort of the general sort of directional covariant directional derivative looks like, right? I should probably put the E sub k here as well, right? So this gives me an actual object. And again, you have to introduce this notion of an affine connection in order to make sense of the covariant derivative. And again, it's like, if you recall, the reason it's like why you want the covariant derivative as opposed to the usual derivative is because the covariant derivative, it's like transforms in a tensorial way, and so it makes sense on a manifold, whereas the usual derivative does not transform tensorially. Okay, all right, so if you have that, it's like I can again write this down, right? So this parallel transport equation, right, looks like C dot I so this is AJ. Okay, and you want this to be 0, right? So it has to be that each component is 0. All right. So okay, so look at this term here. It's like a C dot, it's like partial, because C dot I, partial respect to I of AK, is essentially the derivative, it's like of AK, it's like respect to time, if you will, right? Because you have, okay, so what you have is that essentially you have something like this, right? And this is really nothing more than the total derivative with respect to AK CK, right? Because this is partial of AK respect to CK, right? That's CI, and then the total time derivative of CI respect to t, right? That's just the chain rule, and this is of course nothing more than the CI dot. It's like DI AK, right? All right. So anyway, so that object, right? This thing you should interpret as the basically A dot K. It's like where you differentiate respect to t. Okay. All right. So I should probably have mentioned the same calculation. It's like when we were talking about the geodesic equation. If you recall, we had something very, very similar here, and except that instead of A, it's like you had C dot here, and that combination, it's like became the second derivative with respect to t of A. Okay, of C, right? So anyhow, so this is basically sort of an aside, and it's again just telling you that that particular combination is just going to be the time derivative of A, yeah, along the curve. So this is equal to A dot I. Well, let me just put it A dot K, right, of T plus gamma ijk aj C dot I ek. Right, so for that to be 0, it's like this thing inside the bracket has parentheses has to be 0. So this gives you A dot K plus gamma ijk aj c dot I, right, equals to 0 for all k. Okay, so this is what is called the parallel transport equation. All right, so it should be remarked that in general, this idea of parallel transport of a curve of a vector along the curve is path dependent. Okay, so that is something to be careful about. So in general, right, parallel transport is path dependent. Okay, so so we can denote the parallel transport okay, so before I do that, it's like all right, so if this A of t satisfies the parallel transport equation, okay, which can either be in this component form or just sort of this intrinsic form here, right, then we say that so A at time 0, which is in the element in the tangent space, the C at time 0, right, is sort of parallel transported to A1 in the tangent space at C1, right, and so in general, and this in general depends on the curve. Okay, so I can denote this by the following. That A1, which is the sort of the parallel transport vector at the end of the curve, right, is denoted by pi, okay, along some curve from C at 0 to C at 1, and this acts on the tangent vector at time 0, right? So this just is a shorthand notation for telling you that this parallel transport depends on the initial point and the final point as well as the curve, right? I guess you could just sort of imagine that it depends on the curve itself with an understanding that you're going to parallel transport from, you know, it's like time 0 to time 1. It's like, but, you know, this gives you a little more precision in the notation, okay? All right, so anyway, so this is this idea of parallel transport. It's, you know, conceptually quite closely related. It's like to the discussion we had. It's like in terms of geodesics, as you know, it's like where essentially you have a curve. It's like where the tangent vector in the direction of the curve, it's like stays the same. So now this is you know, very similar. It's like where you start with a certain tangent vector. It's like at initial time, and you want it's like to define, you know, it's like tangent vectors along this curve such that you know, tangent vector doesn't change, so to speak, right? So again, it's like that involves taking the covariant derivative, the directional covariant derivative. It's like of that, you know, it's like parameterized family of tangent vectors in the direction of the curve. It's like and requiring that that vanishes. All right. So let me just stop here for now.